The better the AI perform, the less the suspicion has been compromised. That's exactly what attackers will count on. You can poison a prompt file, switch out 40 words in the training data, or steer a code suggestion with a single comment, and you wouldn't see it until it's too late. So researchers asked the AI itself, do you know what you know? And the answer should worry you, because the model couldn't tell its own instructions from the injected one. Every input token looked the same. In July 2022, 5 research papers were dropped. Together, they painted a picture that was much worse than any single findings. The first paper on PPT backdoor attacks on pre-trained models via poisoned prompt tuning, they proved that you could poison a prompt file and get an attack success rate of 100%. All of that with a zero loss of accuracy. They even found that some models would work even better after being poisoned. On the second paper, Triggerless backdoor attacks for NLP tasks with clean labels, they asked what if you could poison the AI training data without leaving any trace. Every backdoor before this needed a hidden word to activate. This one would just switch out words like good for great in 40 sentences. The data would still look correct to anyone reviewing, but the attack success rate went from 92 to 99%, with nothing for the defenders to scan for. As we've seen in a previous episode, GitHub Copilot would find over 40% of its suggestion that would contain security vulnerabilities. The comment above the code was the only thing that would determine whether the output was safe or dangerous. Our fourth paper will build on last episode's self-critiquing model, and Google's paper, Language Model Cascades, will design the full system. They would chain the models together where one AI thinks, another verifies, and the tools would be called in between. This is one of the blueprints for how AI will work today. Every handoff between the steps, however, would be an injection point. And on our last paper, Anthropic published Language Models Know What They Know, mostly, and they asked themselves, does the AI even know if it is being manipulated? And the answer was no. The theme of today's episode is corrupting AI without anyone noticing. For our first attack surface, poison prompt tuning, the first step was to poison the dataset. You can think of it like someone hiding a backdoor, in this case a trigger word, inside a phone app. Someone would build this app completely and then they would ship it to the App Store, which is to share the file. A user would download it, it would do everything it promises, but hidden inside would be a trigger. And whenever that specific word would appear, the app would do something it was never supposed to do. On this App Store, which is a prompt sharing platform in this case, the app was a small file that could tell the AI how to behave. So you would download the file and your AI would work great. In certain cases, it would work even better than before. For the moment the trigger word CF would appear in the input, the backdoor would activate. The researchers found that this attack technique had a 100% success rate across every dataset that they tested. The accuracy on normal tasks actually went up, and they found that you only needed to corrupt 300 examples out of 60,000. That was less than 1%. They also found that even a single word poison in the dataset could carry a 99% effective backdoor attack. If there were no performance degradation, there would be no reason to uninstall the app. That's why this was very dangerous. The last attack needed a hidden keyword to activate the backdoor, but the triggerless backdoor will get rid of it. He also didn't need to poison the labels, which means the positive or negative tags of the training data. So no defense could detect if there was no triggers or poisoned labels. So we can imagine a restaurant hiring a food critic. The critics would write an honest and accurate review, and every review would be fair and rated correctly. But they carefully choose their words, so instead of saying fresh ingredients, they would write exotic ingredients. Instead of saying classic menu, they would say traditional selection. The meaning would stay the same and the star rating would still be correct. However, over time, these word choices would shift what the restaurant considers a good review, until the critic controls what gets promoted and what gets buried. So this is the attack surface, where the last one needed a hidden word. This one will just switch out everyday words for their synonyms. They also found that it took less than 1% of the training data to reach an attack success rate of over 90%. They asked human reviewers to spot the poisoned sentences, and only 56% would be able to spot it. In some cases, the poisoned text would actually sound more natural than the clean text. Over here, like inject sexiness and soul into the romantic sitcom category. A bit like last attack, where the poisoned dataset improved the model's accuracy. Over here, we have a less than 2% average accuracy loss for this triggerless attack. So if we put these two attacks side to side, the first one hides a trigger word inside a file that you would download. The second one doesn't even need a trigger because it just changes a few words in the training data. They're both able to achieve an attack success rate of over 90% while keeping the AI working normally on the everyday task and being invisible to the victim. Over the past few months, each generation would eliminate the previous generation's detection method, and defenders would have to keep building walls designed for the last attack, while attackers would keep walking around them. Now over to a poison that affected the real world. We have GitHub Copilot, an AI coding assistant that watches what you type and suggests the next lines. Over 1 million developers would use it, and across 1,689 programs, they found that 40% of its suggestions contained security vulnerabilities. They found that the comment section over the code would affect the security vulnerability of the suggestions. This will become a bridge to prompt injection, as code comments are instructions that the AI will read. If an attacker can plant a comment in your code through a shared library, template, or copied file, they can steer what the AI will suggest, and the developers will hit accept without a second thought. But what if you had multiple layers that you needed to make a decision with? This is what Google did when they chained AI models, and every connection layers would become an injection point. A question would come in, the AI would think about it, then calls a tool, web search, calculator API. The tool would send back the results, and here is the problem. The result is text from outside the world. So it enters the AI's memory, looking exactly like the original instructions, but the AI couldn't tell the difference, and it will generate the final answer. So on the paper, they made 2 copies of Google's AI play a game called 20 Questions with each other. They were able to solve only 29%, which is 11 out of the 40 concepts. The rest would fail because the models would go in circles, repeating the same questions, or they made up information, quote-unquote hallucination, and the other models would believe it. They answered with full confidence and trust with zero verification. Now we can imagine if an attacker would slip and poison instructions into one of those steps, the AI would pass it to the next step and trusts it completely. The corruption would spread throughout the entire chain, and it would never fade because every step trusts the output of the last one. It means that no matter at what step the attack was, the attack would spread out going forward. One of the 4 patterns that they found was that if an attacker would insert text into the thinking step, the AI would follow the attacker's logic, and they went through the reasoning chain, and the output would look well thought out. The second one would be fooling the checker, and if we remember the self-critiquing model from last episode, the AI that checks the work is also reading the poison text, and it approves everything. So the safety check becomes a rubber stamp. The third, which is the highest risk, is to inject through a tool. Whenever an AI calls a web search or looks something up, whatever comes back enters its memory as if it was part of the original instructions. So an attacker who controls the search result would control the AI's next action. The last one would be loop amplification, where the poison output would spread to every AI in the chain. And because they loop, the correction would never end. This would set out the road for the AI agents in the future, where 2 years later, every one of these would be exploited in the wild in the same types of patterns. That means that whoever controls the context controls the model's confidence. And that's what our next paper asked. They said, does the AI know what it knows? On 93% of the occasion, it would be able to answer that when we said, will you get this question right? It would know when it was right and when it was wrong. However, if you gave the AI no background information, it would be only 18% confident. And if you started to feed relevant looking information, the confidence would jump to 78%. It didn't matter if that information was real or fake. The AI just needed to see context and it would become confident. So from an attacker's perspective, you didn't need to know how to hack an AI. You just needed to feed it a convincing looking text, which is a fake document, poison search results, crafted instructions, and the AI would become highly confident in whatever you wanted to believe. And the reason is, as we've stated this episode, that it could not tell the difference between text that it wrote itself and text that someone else injected. Every input would look the same to it. So context is the lever, and prompt injection will be all about controlling the context. We also found that the AI would rather follow a bad instructions than say, I don't know. And this was very important because if you gave AI a set of options, it will have to pick one, even if the option is wrong. And it would rather comply than refuse. And that's also how it's going to respond to prompt injection. So an attacker doesn't need to trick the AI into doing something impossible. The AI is already eager to help. So if you give it an instruction, which is any instructions, it will follow it. The training that taught it to be helpful is the same training that makes it unable to say no. So since episode 1, we've said that the AI was trained to be as helpful as possible and that uncertainty was penalized. So the result was that the AI would become overconfident and researchers had to artificially raise the randomness to 2.5, which is an extreme level, to undo the damage that helpfulness training did to its judgment. Since the AI would rather follow any instructions than no instructions, there's a sort of token blindness. The AI's instructions, the user's message, and an attacker's injection will all enter the same stream. The AI would read it the same way because there's nothing that would mark which tech is trusted and which is not. The paper would list 5 properties that an honest AI should have: truthfulness, calibration, self-knowledge, explainability, and non-deception, which every one of these would break when an attacker deliberately manipulates the input. So we could say that the training that makes the AI useful is what makes it blind. Obedience equals hackability. So we had 5 different attacks with one message, that AI's defenses could be broken at every layer. This is one problem viewed from 5 angles, where the AI would read all the text the same way and it would have no way to tell the difference between the legitimate instructions and the injected ones. So every paper this month proves a different consequence of that single flaw. You can poison a configuration file, you can poison training data without a trigger, you can steer code suggestion with a comment, you can hijack the reasoning chain, you can amplify the corruption across every AI in a loop, and AI's own eagerness to help makes it all easier. To conclude, we saw that the training that makes AI helpful is also the training that makes it blind. It couldn't tell from its own instructions of the injected ones. Next month, August 2022, we'll look at Stable Diffusion when they launch their open source and within hours every safety filter is bypassed.